All right, here we are for the this is the third mechanics problem from actually the 2004 exam. Okay, so you can see here we have this rod. It says a uniform rod, mass m, length L. It's on a pivot, right? So you're expecting it to swing at some point. Right away you're thinking rotational motion is probably your first gut instinct with this. Just looking at the picture, right? Okay, I can see here's a picture of it hanging vertically. Okay, anyway, and the pivot, good enough, moving on. It says, okay, uniform rod mass M length L is attached to a pivot of negligible friction as shown above. The pivot's located, you see, a third of the length from the left end of the rod. Express all answers in terms of the given quantities, M and L, and fundamental constants like G. Calculate the rotational inertia of the rod around the pivot. Okay, so if we're going to spin this around the pivot, find our moment of inertia. So take a look at this one. There we go. So this is the 2004, and it's like the third problem. So I want to find the moment of inertia. So that's I, right? And we know that I, when it's a distributed object, like it's got a shape, right, like a rod here, then we know our moment of inertia is going to be the integral of r squared dm. Okay, until we've added up all little bits of mass. So we're going to take that rod, right, and the pivot is there, L over 3 away from the left end, right? The whole thing, of course, has a length L, right? And we're going to be, that'll be our axis of rotation. And so you say, hey, I know I want to take this and slice it up, slice into a whole bunch of little DMs, right? Okay, so we're going to take this guy and slice, right? Okay. Each one of these little slivers, right, has a mass, dm, and it has a little length, little width, right, which you could call that, if you want, we could drop an x-axis down and call that dx. That's what I usually like to do. Get it in terms of coordinate axes is what I usually like to do, right? So I drop like an x-axis here. I would call this here x equals 0. So we're going from x is maybe negative L over 3 to x is 2L over 3, 2/3 of L, right? The whole thing's L. It's probably what I would do. And so this has a little dx, right, which is actually like a d length, right? A little dl, right? D length of it, right? It is, I will side comment say, it is unfortunate they're using capital L for the length. We've talked before about capital L being angular momentum. I don't think we're going to use that in this problem, but you know, if we did, that would be really awkward. So, woo, I would rather use cursive lowercase l for lengths, but what are you going to do? All right. So I'm going to do this. So if I did this integral, I would want to go, first of all, I'm going to say a little dr. R is like the distance from the axis, right? So like basically R is just my distance from here. I made that x equals 0. So whatever my x position is, that's my R position. That's my distance from the axis of rotation also. So this is really turned into x squared dm. You know what I mean? If you want to think about it that way. And we're going to do this until we have the whole mass, right? This whole thing is a mass big M. All right, so I need to change this to be from in terms of mass to an integral in terms of x is ideally what I would want. I'm going to go ahead and use my linear mass density. That is my mass per length. They tell you that this is a uniform rod, and that means that my mass per length is a constant value all the way through the rod. It's the same density everywhere, same linear mass density. So if I took half the length, I would have half the mass, fourth the length, fourth the mass. If I took a little dm, I'll have dl will be dm. So that'll be like dm over d length, right? Now d length, that's the same thing as a dx, right? So dm to dx. Let's say that lambda times dx is dm. So this is what I would substitute in for dm. So I'm going to change the variable of integration here from dm to dx. X squared lambda dx, right? It's my substitution there, right? I'm going to do this now. My bounds, instead of being from 0 till I have all the mass, all the slivers of mass added up, my integral now is in terms of x. From x is negative L over 3 to 2L over 3, 2/3 length, right? Okay. Lambda is a constant, so it'll kick out of the integral. So now I just have my integral of x squared dx, and you say, hey, that looks like an integral that I can handle, right? You said it'll be 1/3 x cubed evaluated from negative L over 3 to 2L over 3, right? Now that lambda out in front, lambda is not a variable that they gave me, so I need to get it back in terms of the variables they gave me. Lambda is just m over L, my mass per length, all right? And things are looking good, right? Final minus initial when I substitute in for that x cubed. So this will be, what do I got here? I got 1/3 m over L, and then x cubed. Final minus initial. Final, that's going to be like a negative L cubed over 27 minus an initial. When I cube that, I'm going to get negative 8. I'm sorry, I'm going to get positive. Sorry. I'm going to get 8L cubed over 27, right? Okay. That's strange. Yeah, sure, that's just life. Okay. So when I do this, I'm going to get, these are both going to be negative terms. They're going to add together. So I've got 8L cubed over 27 plus 1L cubed over 27. That's going to be 9L cubed over 27. Or if you like, 9 goes into 27 3 times. So that'll be like minus 1/3 L cubed, right? Now, I just did this totally backwards. Final minus initial, right? This is the initial. That's the final, right? Sorry about that. So that's positive. And it should be minus the negative, right? Which is going to make it positive. Okay, sorry about that. This is going to be positive there. Okay, I didn't think I should get a negative sign. Okay, we're all good. Sorry, I got the order backwards. This is going to be positive, right? Minus, and then it's going to give me a negative. Minus a negative makes it positive. Okay, we're all good. All right, when I flip the order. Sorry about that. Okay, hey, L cubed L to the first power. You can see I'm going to get 1/9 ml squared is going to be my I value, right? Okay, so that's that. All right, let's see here. There is actually like a cheesy, faster way of doing this one, but it requires you to have memorized a couple formulas. Okay, the cheesy way of doing it is to use the parallel axis theorem in reverse. So if you happen to know that the moment of inertia for a rod through its center of mass is 1/12 ml squared, if you happen to know that, you could use the parallel axis theorem, Pat, and you could say, hey, I know that my I new is I center of mass plus md squared, right? Where d is the distance we've shifted the axis parallel to the original axis. So my new I would be equal to the I through the center of mass, 1/12 ml squared, plus the mass times the distance we shifted it. Now we went from the middle, the center of mass is the middle, and if I go to here, that's 1/6 of L over, isn't it? I know, you're like, yeah, take a second, convince yourself. This distance we shifted here is L over 6, right? Because that's 2, 6, 2, 6, and 1, 6 would be 3, 6. That would be half the rod, right? That makes sense. Okay, so this D is 1/6 of L squared. So my new I is going to be 1/12 plus, and when I square this, can you see that's going to be 1/36 ml squared? Let's see here, and 1/12, that's 3/36. So 3/36 plus 1/36, that's 4 over 36. 4 over 36 is 1/9. So again, you get 1/9 ml squared. So that's an alternate way of doing it, but it requires you to have this memorized. And of course, you got to know the parallel axis theorem, but we're expecting to have to know that and kind of work backwards. Backwards? Not really backwards. It's just happening to know that. Okay. So anyway, that's part A. All right, let's go on to part B. Part B says, okay, the rod is then released from rest in the horizontal position shown there. Find the speed of the bottom end when it passes through the vertical. It says it swings down, right, as it passes through vertical. How fast the linear speed of the bottom end. So I'm going to grab another sheet of paper. So I got some space to work. All right. So we know this thing is going to and our pivot point is at L over 3. It's going to swing down. So it'll be like this, right? I didn't draw that perfect, but you get the idea. All right. So we're kind of swinging down, yeah? And we want to know a point at the end of the rod, what that speed is when it gets to vertical. All right. So we're trying to find this tangential velocity there, right? Okay, that V. So how are we going to do it? Well, we've got gravity as an outside force tugging on this thing, making it swing down, making it get faster and faster. That outside force, it's going to be exerting a torque, a twist to change the angular momentum. So the angular momentum is not going to be constant. There's an outside torque acting through a distance. Not only that, that torque will be changing in an awkward way because the angle between the gravitational force and the motion is, and the lever arm would be changing all the time. So we're not going to do angular momentum for this. This to me, pulling this along, hey, we're going from 0 to some, we're speeding up faster. Can I use kinematics? And say if I go to do kinematics with like, the rotational quantities, alpha, omega naught, omega, and delta theta, and t. If I want to do that, to use the kinematics equations, you need a constant alpha, right? And because the torque will be changing, because while it's swinging along here, I'll draw an in-between point. While it's swinging along here, yeah, you would agree that I'm going to have gravity. I'm going to draw gravity acting at the center of mass, right? That's going in an arc, right? You know what I mean? And the point is that angle between the gravitational force and its lever arm, its moment arm, an axis, a line from the axis of rotation to the point where the force is applied. You see the angle between those is changing all the time. So my torque, which is R cross F, you say because of the sine theta hiding in there, that's changing. And so we're not going to have a constant torque. So doing, some of the torques as I alpha would be awkward, right? We can't use kinematics. We don't have a constant alpha. We got to change in torque. It's like, our only choice really here is to use energy, okay? Is really the way to do it. We could write some kind of equation for this torque as a function of theta as it goes from this angle to this angle. It'll be easier just to use potential energy. So that's what we're going to do. So we're going to do conservation of energy here. And so we're going to say sigma W, right, is delta K. We're going to make our system be the rod and the Earth. So that means I'm changing the distance between them. I can have a delta UG term. Okay, well now the only outside force on the system is just gravity and a force from the pivot. You see that force from the pivot, right, that's tugging on it, right? Force from the axle, that normal force from the axle, that's not going to do any work. It's not pushing through a distance. And so I can say, oh, there's no work term here. Okay. So you're like, okay, K final minus K initial. But at the start, the starting speed was 0. So K initial drops out. Bam, right? And then we have UG final minus UG initial. And you're like, well, where do you want to call height 0? Do you want to call now again, we're talking about when we do heights for gravity, we're going to use for gravitational energy, we do the height from the center of mass, right? Remember, this is at L over 3. This is just a 6th L over, right, to the center of the rod, right? So this is only dropping down from here. This is the distance from the center of the rod. That's just L over 6. I'm going to call the final height 0. Let's call this height 0. And so then my initial height would be L over 6. All right, so my final height is going to be 0, so this term drops out. This is going to be fine from here on out now, right? Okay, and the kind of kinetic energy we're looking at here is rotational kinetic energy. So that'll be 1/2 I omega final squared, right? And then I just have minus mg and the initial height, which was L over 6. Okay, the I, we already figured out the formula for rotating this guy around that pivot. Is, getting ahead of myself there. That I is 1/9 ml squared. Now, you notice that what this is going to get me is it's going to get me an equation for omega. And from omega, I can find V. So let's do this. You might notice right off, well, let's just do the math. Let's do the math. I'm going to cancel out mass out of each term, though, right? I'm going to try to find omega. So I'm going to move this over here. So I'll have GL over 6 is 1/18 L squared omega squared, right? Move this to the other term. Oh, look, I can cancel an L. All right, cancel an L out. Bam, bam, right? So you see what I'm going to get? I'm going to get 18 over 6. That'll be 3 G over L. And take a root, and that'll be omega final. Okay, because 18 over 6 is 3. Looking at this units-wise, G is in meters per second squared, and L is in meters. So I'll just get a per second squared. Then I take a square root, so it'll just be seconds per second, which is the unit for angular momentum, radians per second. Angular velocity, wow. So anyway, moving on. So that's that. You say, but we want to find the speed at the end. How do I do that? Well, V is our omega, right? Okay, but the R here, we're talking about at the end of the bar. What's this distance? Remember, this is 1/3 of L, so this is 2/3 L. I didn't draw this to scale well at all. So that R is 2/3 L. And then omega was the root of 3G over L. Okay, so that's my V. This is a little ugly, the way I got an L outside and an L inside and a 3. I can probably make this tidier, don't you think? Yeah, I can probably fix the L problem. If I move this L inside the radical, it would be an L squared, right? From outside, it's an L squared under a radical. Take the square root of an L squared is L. So that L squared will cancel one of the L in the bottom. And so I'll just get 2/3 root 3GL. And you say, gosh, that is a lot. That is tidier than that. And that's probably what they'll want to see. All right. All right, how do I feel about that? I feel pretty good about that. Okay. You know, they may want us to combine the 3 inside and the 3 outside, right? If I had a 3 outside, I can move it inside in the denominator as a 3 squared, and that would cancel 3 on top. Gosh, would they like that better? 2 times the root of GL over 3. I don't know. I know they don't like having radicals in the denominator, but I don't know. Maybe that's better. I don't know. They're the same thing. I think they would accept either one. That's not too far off. I would accept either one. All right. I don't know which one's nicer. Okay, but that's what I would do. All right, so that's part B. All right, which takes us on to part C. Okay, the last part of this free response problem. Part C says, okay, it's swung down, right? It was oscillated. Okay, now we're going to let it come to rest. Okay, and then we're just going to displace it slightly, just a little, and then let go and let it swing back and forth. Find the period of oscillation as it swings. Now, you don't need me to tell you that this is what we call a physical pendulum. Okay, and so its period of oscillation will be the same even as the oscillations die down. But we remember there's this. Why does it matter that it's displaced slightly? Why don't they just like drop it from here and have it oscillate back and forth? Well, you might remember that part of that derivation for the period of a pendulum involves using the small angle approximation for sine. And so it really only acts like a simple harmonic oscillator for small oscillations. So that's why they're doing it that way. Okay, but anyway, they want you to go ahead and calculate the period of oscillation. You're like, hey, the formula for the period of a physical pendulum is not on the AP formula sheet. They're making you derive it here. Okay, so we can do that. Okay, so let me grab a fresh sheet of paper. That's right, we're going to page 3 for this problem. They're making us derive all kinds of things that we hoped we could just do simply. But here we go. So this free response problem with only 3 parts, right? So you kind of expect them to be big. Here we go. Part C. So we want to find the period for a physical pendulum like this. So I'm going to draw this out. Okay, and I'm going to draw this at some, not a special position, but some random angle here, right? So we're looking at this, and we're thinking to be a simple harmonic oscillator, I have to have this linear restoring force that tries to push it back to equilibrium, which would be vertical, right? So that force that's going to act on it is just the force from the pivot that exerts no torque. That's not going to try to twist it back anywhere. It's going to be gravity, the gravitational force acting here. Does this look like a vertical line? I tried. That's the gravitational force. I know that I'm going to find that torque from gravity trying to restore it. There's my R vector. Hey, the R vector here, that's just L over 6 again, right? From the center, that's how far off the center mass we are. So when I do this, remember how this works. We're going to do sum of the torques is I alpha. For most simple harmonic oscillators, we do sigma F as MA, but for things rotating back and forth like this angle, we use some of the torques. My only torque is that torque from gravity, and that torque from gravity is going to be equal to I alpha. Hey, the I, we actually have a formula for. We figured out it was 1/9 ml squared, remember? And alpha, sure, I'll look about that for now. Let's figure out our equation for torque. Torque is R cross F. So the R is L over 6. The F is mg. And then there'll be a sine theta there, right? Okay. Okay. And that alpha we could rewrite as second derivative of theta with respect to time. And you're like, okay, now I know the simple harmonic oscillating pattern is that I have a negative constant times my displacement variable, right? Equals the second derivative of the displacement, the acceleration. So to get to that form, I would move this over here. We can see that the mass will drop, bam, bam. One of the L's drops, bam, bam. That 9 and that 6 I can tidy up and make a 3/2 G over L sine theta. And you say that's pretty close to a simple harmonic oscillator. We just need to make a couple adjustments. One is we know that this torque, if I call the angle that I twisted this through, if I call that angle there, theta, then my R vector is going this way. The angle between R cross F, that's sine theta, that's the angle between the way R is going and the way F is going, that's this angle. Okay, and that's the same as that angle of displacement there. What we're going to do, and I know that if I'm displacing this way, the torque from gravity, right, R cross F is trying to twist it the other way. So I'm displacing it this way into the page. The torque from gravity, R cross F, is out of the page. So it's going to be in the opposite direction. The acceleration is opposite the direction of the displacement. And that's going to matter because in a second, we're going to replace sine theta with theta. Again, that's the small angle approximation for sine. And so now I just have this. And you say, hey, that is the simple harmonic oscillator pattern. And when you do this, remember the coefficient in front of your displacement variable, that is omega squared, the angular frequency, right? And the period is 2 pi over omega for any sinusoidal function. And so you say, hey, it's going to be 2 pi over the root of 3/2 G over L. Let's get that fraction out of the denominator and tidy it up the way mathematicians like to see it. So we're going to invert it, put it on top. So it'll be times the root of 2/3 L over G. Okay, now I have a 2 outside and a 2 inside. So they probably like me. No, because if I do that, it'll be on top also. We're not going to make that an 8 in there. That's not tight here. We'll leave it like this. Okay, so that's it. So that is my period of oscillation for that physical pendulum, right, is what I would do. All right. Hey, that's it. That's that problem.